Hello, my name is Aki. In the previous finite state machine videos, I briefly mentioned that finite state machines or FSMs do not scale well, and that for more complex behavior, we should consider using a hierarchical state machines or behavioral tree. In this video, I want to focus on the finite state machine problem, specifically when FSMs start to fail and why they scale poorly as the project grows. I will also talk about hierarchical state machine and explain why it is much more better solution for handling complex behavior. The problem with finite state machines is that as a project grows, FSMs become harder to manage. The core problem is that every state must handle transitions that can happen from any other state. To see why this is an issue, let's take a look at a player character example. Let's say that the player can be grounded with states like idle, run, and crouch. Also, the player can be airborne, like jump and fall. On top of that, the player can become dead or be poisoned. The player being poisoned takes damage over time, but can still move. This means that the player can be poisoned while idling, running, jumping, or falling. And this is where FSMs starts to fail. In FSMs, each state must check global conditions, such as death. So every state ends up doing something like this. This logic must be repeated in idle, run, crouch, jump, fall, and every new state you add. As a result, you get duplicate logic everywhere, which quickly becomes hard to maintain. Another problem is what happens when the player is idling, running, jumping, falling, and becomes poisoned? Which state should they be in? There are two common options. Option 1 is to create states like poison run, poison idle, poison jump, and poison fall. However, every new overlay conditions multiplies the number of states. This is known as state explosion. Option 2 is to keep the original state and add conditions inside it. But now every state contains extra conditional logic. At this point, you are essentially rebuilding a hierarchical state machine inside an FSM, but in a messy and fragile way. Because of this, FSM does not scale well. For example, imagine adding another effect like burning. You would need to duplicate the logic again, or create even more combined states. Maintenance quickly becomes a nightmare. FSM especially struggle when many states share the same transitions. Effects overlap movement, and multiple conditions are active at the same time. So, how do we solve this? The solution is to use a hierarchical state machine, or HSM. An HSM allows states to be organized into parent and child states. Parent states handle shared logic, and child states handle specific behavior. First, shared transitions are defined once. For example, the alive state handles logic like this. All child states inherit this automatically. There is no need to repeat this logic in idle, run, jump, or fall. More importantly, poison is no longer in a movement state. Instead, we create a separate layer that can be run concurrently with a movement. This allows the player to be idle while poison, run while poison, jump while poison, and fall while poison. This behavior is very difficult to model with FSM. Let's compare the number of states in both approaches. With a finite state machine, we start with the basic movement states like idle, run, crouch, jump, and fall, which gives us 5 states. Since the player can also be poisoned in each of these, we need 5 additional poison versions. Adding a dead state brings the total to 11 states. Now, if we introduce another global effect like burning, we would need to duplicate those 5 movement states again, increasing the total to 16 states. With a hierarchical state machine, the structure is more efficient. We begin the shared parent states like alive, grounded, and airborne, which gives us 3 states. On top of that, we have the individual movement states like idle, run, crouch, jump, and fall, adding 5 more. Including a dead state brings the count to 9, and adding a poison layer, making it 10. If we later add a burning effect, we only need 1 additional layer, resulting in 11 states in total. From this comparison, we can see that for simple movement logic, an FSM is not a bad solution. However, once global conditions are introduced, FSMs scales poorly and quickly becomes difficult to manage. Each new global effect effectively adds 2 times the number of existing movement states. In contrast, with HSM, we only need to add a single new layer. The key takeaway is that FSM is simple and great for getting started, but it does not work well when states share transitions, effects overlaps behavior, and complexity increase. As a result, if you find yourself copying and pasting the same logic into many states, it is time to switch to hierarchical state machines. HSM scales better, is easier to maintain, and models complex behavior in a much cleaner way. To summarize, finite state machines are simple, easy to understand, and a good place to start. However, as soon as a project grows and more global conditions are added, such as the player being poisoned or burning, FSMs quickly become difficult to manage. Every state must handle the same transitions, which leads to duplicated logic, state explosion, and poor scalability. Hierarchical state machines solve these problems by organizing states into parent and child relationships. Shared logic, such as taking damage or dying, is defined once in a parent state and automatically inherited by all child states. In addition, effects like poison can be handled as separate layers that run alongside movement instead of replacing it. As a rule of thumb, if you find yourself copying and pasting the same logic into many states, it is time to switch to a hierarchical state machines. HSMs scales better, is easier to maintain, and models complex behavior in a much cleaner and more flexible way. Thank you for watching. If you find the video helpful, please give a thumbs up and subscribe. If you would like to support the channel, you can find the links in the description below, and I will see you in the next video. Bye bye.